What is the directional derivative? Well, again, try to draw a manifold first. Let's try to draw a manifold and we'll try to see. So this is our manifold, and since we have defined what are functions, we can try to define a function on it. Obviously this can be thought of as an n-dimensional manifold. For simplicity, I'm considering R3, that is a three-dimensional manifold. Our M is just R3. So what we can do right now, we can define function on this manifold, right? And that function would take in 3 arguments, and for simplicity again we can think of this manifold as the three-dimensional Euclidean space. So we can define a function like f of x, y, and z for simplicity, but this procedure would also work when there are n-dimensional manifolds and you have n variables, so to say. So as you can see that in real variable calculus we had only 2 ways to go, that is we can go left or we can go right on the x-axis, right? But here on the manifold there are 3 degrees of freedom. So I can either move in x, I can either move in y or z, or I can move in between x, y, z. So there are more degrees of freedom. So now what we do is that since we know that we can even define vectors as well on a manifold, so let's take a point. Let's say the point has this arguments x0, y0, and z0. The point itself is P, and we try to find a derivative. That means we want to see how this function changes. Let's say the derivative along this direction. This is a vector, so let's call this vector u. And a new way to write our vectors on this manifold language would be to write it as a column vector. That means a column matrix. And let's say it has elements of A, B, and C. If you write it in your high school language, this would look like AX hat, BY hat, CZ hat, like this. Alright, so this is our vector, and we want to see what happens to this function. That means how it changes if we go on to this direction, if we move into this direction. So this is the motivation behind defining this directional derivative. Now the formal mathematical definition that people usually see in their vector calculus course is something like this. So this will be the vector calculus definition of the directional derivative. It is denoted most of the time as du, capital Du. U means along the lines of the vector u, that means in the direction of u. Our function is f of x, y, z, and it is defined as the following. T goes to 0. This is f of x0 plus at, y0 plus at, z0 plus at, minus f of x0, y0, z0 divided by t. So what is this t? This t is nothing but the point over here, some p prime, which is denoted as x0 plus at, y0 plus bt, z0 plus ct, like that. Oops, sorry, it should be b and it should be c, not a. So this is the definition, and this can be written in a more compact form using the vector notations, and that compact form is nothing but limit t goes to 0. This is just f of p plus u t. Note that p itself contains 3 arguments, or so to say a vector as well on that point. You can think of it both ways. Minus f of p divided by t. If this limit exists, then the value of this limit evaluated at point x0, y0, z0, which corresponds to t equals to 0, would be the directional derivative. Okay, but working in this way, it becomes a bit tough to evaluate these limits. So what we do right now, we have to do a little bit of algebra to simplify this definition. So let's try to simplify this definition, and we want to see that whether we can actually compute something that is easier to do than evaluating this limit. So from this line, let's call this equation 1. From 1, we see that the directional derivative is given by limit t to 0 f of p plus ut minus f of p by t. Now this is what it almost looks like, a derivative that is analogous to a real variable function. I mean a single variable function. So what you can do right now is that since you are trying to evaluate the directional derivative at a point p where t itself is equals to 0, you use this definition and you write it as ddd of t, where this acts on p plus ut, and then finally you put t equals to 0. So what is the advantage of this thing? Well, recall the fact that we can write a total differential of a function or a multivalued function as follows. Since we are considering three variables, so d of f of x, y, z, we can write it as the partial derivative of f with respect to x with the dx, that is an infinitesimal change in the calculus perspective, but we will later see that these are actually one forms, which you will see in the next lecture. So this is one thing. Then you have df of dy, and finally you have df of dz, and all these deltas, they mean partial derivatives. So finally you have this guy. So you can use this over here and use the fact that p and u, they actually contain three entries, both of them. So by doing that, what you are actually doing is writing it as f of p1, or so to say that x0 thing. So whatever you want to write it, if you write it as x0, just the thing over here, x0 at, and x0 plus at, and let's call this a new variable as x1. So by doing this, what I can do right now is that I can use some tools from multivariable calculus to simplify my calculations. So these are x1, x2, x3, like this, right? And they're evaluated at t equals to 0. Now you can use the chain rule. So at this point we are using the chain rule. So that means you will have a partial derivative of f with respect to x1, and x1 would get differentiated with respect to t. Similarly for the other parts as well. Now, what was x1? x1 was equals to x0 plus t a, right? And dx1 of dt is nothing but a itself. Similarly, you can show that this is a, what we just showed, and similarly we can show that this is b and this is c. So we finally have df of x1 multiplied with a, then b multiplied with df of x2, and c with df of x3. So if you can calculate partial derivatives, you can use that power to calculate directional derivatives as well. In fact, directional derivatives reduce to partial derivatives. And you can easily see that if you consider the vector u as a unit vector, that is, u was written like this, right? A, B, C. Now, I am only interested in the directional derivative segment where the direction is only along x1, let's say. So that would mean that I'm not looking what is happening over the other axes, that is x2 and x3. That means I don't care about those variables or coordinates. So the direction vector, that is u, will contain only one element, and it will be 1. Instead of a, you will have a equals to 1, and b and c would be 0. And if you do that, you will see that the only term survives will be this one. So this is how a directional derivative generalizes those partial derivatives. And as a special case, you get the partial derivative back if you use the special conditions. And there is another remark, is that these vectors can be unit vectors as well. And the reason is kind of arbitrary, because if you keep these vectors as unit vectors, that means the modulus of those vectors are 1, then you can define the directional derivative, but at the same time you also retain the definition of tangents. So that's one motivation to keep those vectors as unit vectors. So this would be our final formula for computing directional derivatives. F of x, y, z is given as del f del x a del f del y. I'm just using x1 as x, x2 as y, but you can keep x1 and x2 as well. See, where u was written as a, b, c, like this. And this idea can be generalized into more variables with more general manifolds or higher dimensional manifolds, or even lower dimensional manifolds as well. Okay, now that we are almost done through our definitions, there is a one last thing that we need to see, and that will be very important for the emergent of differential forms. But let's now try to do a numerical example of these directional derivatives. So let's consider an example. So we want to see an example, and in our example our function is just a 2-variable function given by x cubed minus 3xy plus y squared. We want to compute this quantity at p equals to 1 comma 2 with u is equals to cosine pi by 6 sine pi by 6, right? So all we have to do is that we need to just use the formula that we derived a few minutes ago, and we'll be good to go. So first things first, we want to compute the partial derivatives. So when you are differentiating with respect to x, you treat everything that is not x as a constant, including the y's. So df of dx will be just 3x squared minus 3. df dy is just minus 3. Oops, there should be a y. Yeah, there should be a y over here. And df of dy would be minus 3x plus 2y, like this. And now this can be thought of as a, this can be thought of as b, like we derived in our formula, and we can finally write that this is nothing but df dx a plus df dy b, which is just 3x squared minus 3y times cosine pi by 6 plus 2y minus 3x sine pi by 6. And remember that we have to use the point, because in our definition we were saying that okay, t was equals to 0, but t was only equals to 0 when these 2 points coincided. So now we have to use the information that we are interested in this directional derivative at point p equals to 1, 2, and since this is the Cartesian coordinate system, x will be 1 and y would be 2. So now we have to use that as well. So using this point p equals to 1 comma 2, we put x equals to 1 and y equals to 2. So if you put that, this is just 3 minus 6 cosine pi by 6 plus 2 minus 6 sine pi by 6. So that means this is just minus 3 cosine pi by 6 minus 4 sine pi by 6. Alright, this is your directional derivative at that particular point. Now let's talk about the last thing that will help us in understanding the emergence of differential forms, is that we have seen the directional derivatives definition from the vector calculus point of view, right? What we can do right now is that we can define this directional derivative in another way. So this is the new version of the definition of the directional derivative. So this is the new definition, so let me highlight it. New definition or alternative definition / alternative. So this definition tells us that let f is such a function that works on a manifold and the image is the real number, be a real valued function on a manifold Rn. Then if we have a vector Bp which is tangent to a point, so this is our function on a manifold, n-dimensional manifold, and let Vp be a vector, I mean tangent vector at a point P on that manifold. That means M, that is Vp belongs to the tangent space of that manifold. You can also specify the dimension by writing r to the power n in the bracket. If this is true, then the number which is defined as Vp acting on the function which is defined as this number is our directional derivative. Now you can already see that on the right side we have the same thing that we saw from the definition of the vector calculus itself. So you might think, okay, why are we doing this if we already know that this definition is there, right? So there is another reason for doing it, and you will see why. So from our previous result over here, this one, to be precise. Let's call this equation A so that we can reference it back. You can see that not only this derivative contained this partial derivatives of the function, this rational derivative not only contained the partial derivatives, but also it contained the components of the vector, that unit vector. And now the difference is that instead of unit vector, we are saying that okay, there should be a tangent vector, okay, that is on that manifold. So similarly, just like before, we can write it as df dx1 v1, where I'm assuming I'm working on an n-dimensional manifold, right? And it will have components as v1, v2, dot 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 v of n. And I'm also assuming that my vector space is also n-dimensional, even though that's not the case always. In fact, it can be larger or it can be smaller. But for now, for simplicity, I'm just saying that the dimension of the manifold and the dimension of the tangent vectors, they're same. Though that is not the general case, and even we will see that most of the time this is not the case. So if I write it like this, da 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 f x of n b of n, then under a summation symbol I can write this thing in a very compact manner, that is v of I df dxi. Note that these v's are just components, that means they are some numbers, right? So what does this tell us? This tells us a very interesting thing. Let's consider again. So let's take a special case. Special case of R3. So when it's R3, you will write it as x, y, z, and finally you will have v1 partial of f with respect to x, v2 partial of f with respect to y, v3 partial of f with respect to z. Now this was defined as the tangent vector at that point P, and it is acting on the function. So this third bracket thing is also used to denote that this is indeed a function. Okay, so this is another way of denoting stuff. So now what you can do is that instead of these VPs, that means the tangent vector at some points, what if we take the unit vectors? So now let's take the unit vectors. By unit vector I mean the basis vectors of x, y, and z. That means x hat, y hat, z hat. So here we are going to use a more general notation. Instead of x hat, we are going to write it as e1. Instead of y hat, we are going to write it as e2. Instead of z hat, we are going to write it as e3. So whenever you see this e1, e2, z3s, you should understand that they are the basis vectors. And what are basis vectors again? These are the fundamental vectors that you need to make up any vector inside a vector space. Okay, so if you do that, and these vectors have these components, e1 as 1 0 0, e2 as 0 1 0, and e3 as 0 0 1, like this. All right, so if you do that, you can easily see that e1 of f will actually give you v1, and you want to have this partial of f with respect to x, but since the component is v1 of e1 is actually 1, because this one can be regarded as the v1 component, this is the v2 component, this is the v3 component, right? Just like this. So Instead of v1, you would just write 1. We usually don't write the multiplication of some object with 1. So from here you can see that you are taking a function, then you are using some mapping on that function which is e1, and finally this mapping is giving you an output of the derivative of that function with respect to that basis vector. Similarly, e2 would generate df of dy and e3 would generate df of dz. Now comes a remarkable conclusion, is that by judging with these things, you can think this as an operator, that is, it is acting on something and it's giving you something else, and these are partial differential operators, right? So you can write it as del y of f like this. You can finally conclude that these basis vectors are nothing but the differential operators themselves. At first, this may look very weird and shocking, but this is in fact how basis vectors are defined in multivariable calculus. In multivariable calculus, these are just defined and there is no way to see how this comes in the first place. But once you adopt the language of manifolds, this is emergent, that it comes very naturally. So this will be a pinnacle in our upcoming discussions, where we will discuss about one forms which will be actually dual to this differential operators, and they are nothing but dx, dy's and dz's. So this will be it for today, and I'll see you guys on the next lecture. Thank you.